Now that we've looked at symmetric key and asymmetric keys and PKI, we can now talk about what kind of things need to go into an embedded device. An embedded device needs to be provisioned from the factory with some secret keys. Ideally, each device has a unique random secret key that's different for that device, and that's going to be a way to do public key cryptography. It should also have a manufacturer public key so that it can look at firmware images and know that a firmware image has been signed by the manufacturer to check its integrity. Now, the manufacturer public key can be the same on every device because if you're using digital signatures, knowing that public key does not enable you to forge different program images. So the way you would use this is the device secret key would be used to encrypt outgoing messages. Obviously, that's coupled with a public key, but the secret is the part you have to keep secret. There's probably also a device-signed public key to tell the factory your public key. So this is a public key signed by the factory that you can send back to the factory in communications to say, hey, I'm device number 73, and by the way, here's my public key. And because you, the factory, signed it before I was manufactured, you know that I'm not lying to you about being device 73. Sometimes companies say, oh, that's okay, we'll keep a database of all the public keys of all our devices, but those databases always have a problem. They go stale, something gets scrambled, data gets lost. It's much smarter to have each device be able to tell the factory its public key than to try and keep a record. And there's also a factory public key, which is used to receive messages and updates from the factory. So you have a secret key to encrypt outgoing messages, a public key for the device that the factory's already signed so the factory can say, yes, you're one of the family, and a factory public key so that you can verify firmware updates and other messages. Once you've provisioned the device with these secrets, you can then use standard ways of doing key exchange and bootstrapping communications. Typically what you see is an initial exchange of messages is done with an asymmetric cryptographic algorithm using public keys. Now that's computationally expensive, so you don't want to send a lot of data that way, but what you do send is you send a couple messages up front to set up a randomly selected symmetric key. Alternately, you can use a public cryptography-based key agreement protocol such as Diffie-Hellman. This picture uses an analogy with paint colors to say there's a common paint and a secret color, and you can send these paints through the mail, and even if everyone knows what the color is, they can't separate out the secret from the common paint. And then using this color exchange, you can agree on a common shared secret. Obviously, that's an analogy. You would perform that message exchange. When you're done, you're left with a random number known to both sides and no one else. You then use that as a key for a symmetric cryptographic channel. Those are called session keys because each communication session you generate another random key and use that for the duration of the session.